Is it on? Can everyone hear me? Okay. Yeah, thank you very much. Thanks for the introduction. I'm the chief scientist for QuantumBlack, and this was originally going to be Simon's talk. He's sorry that he couldn't be here. And I think what I want to touch on in this talk is really a point that Ed just touched on, is perhaps how surprisingly applicable a lot of generic data modeling techniques are to solving a broad swathe of problems. So, have a lot of you here heard of Moneyball, the book by Michael Lewis, or seen the movie? So the idea there, the story there was about the Oakland Athletics manager, Billy Beane, and his applying basically sabermetrics, a sort of evidence-based method of analyzing baseball, and looked at, and this was derived, I mean, one of the big proponents of that was Bill James. And the idea behind that was to use data to help address the problem of how do we build a baseball team. Well, effectively, that's a lot of what we are doing. We are not as regards baseball, but we're looking to use data to solve hard problems. And a lot of what we do is made possible by the fact that increasingly data is available. And the amount of data has largely, the amount of data that we can generate, that we can capture, the economics of that have changed dramatically. So it's very easy to acquire very large data sets, to sense things at very high frequencies. And a lot of Big Data Week, I mean, I'm sure has touched on this, that concomitantly with our ability to accumulate all this data has been our capacity to deal with this data, to process it, to manipulate it, to build models that use all of this. So this is a lovely paper that I recommend everyone read who isn't familiar with it, by Halevi, Pereira, and Norvig. It talks about the unreasonable effectiveness of data. That's effectively what we are exploiting in all of our analysis. It's the fact that for many, many problems, many hard problems, the more data you have, the greater the benefits derived from having more data. So there's sort of these superlinear effects that come into play. And this paper really looks at this in the context of one problem, which is natural language processing. And the application of non-parametric modeling techniques to solving hard problems in that space. And so what they look at is two very different camps. Most of the literature, most of the academic literature in NLP had focused on, had looked at very small, relatively curated, annotated data sets, and looking at very structural models, grammars, to solve these problems. And in stark contrast to that, you have, let's say, the likes of Google, which looked at throwing loads of data at the problem and then applying very different kinds of modeling techniques, so largely non-parametric modeling, what are colloquially called machine learning models, to help solve the same problems. And the fact is that these are models that, given enough data, tend to perform much better than the structural models on smaller data sets. So if there's 2 points that, let's say, I want to really emphasize in this talk, it's one, that there is much more data about things, about certain processes, about certain phenomena, where even a short while ago, there was no data whatsoever. It was very hard for us to be able to measure certain things, at least at the right frequencies, perhaps. So we didn't have, let's say, the right proxies against which to build certain models. And I'm talking about problems, for example, like, well, I'll mention a few case studies specifically, but think of all the problems related to, let's say, human resource management as an example. Like, these have for the most part, been kept by, well, we've deferred to people with managerial expertise with lots of experience to solve these problems. And we can now look at data to help inform the analysis of these problems, to apply perhaps a little bit more rigor, even, let's say, to be a little bit more scientific in the application, in the analysis of these problems, in much the same way that companies have been doing for a long time in looking at things like inventory control or supply chain management. And to the extent that that's true, then a lot of the gains from more data, I think, are going to be democratized, are going to be commoditizable. So one of the points that I want to impress upon everyone is that a lot of the analysis for a lot of problems, about 80% of the gains will come at 20% of the effort. So I think the first two case studies are going to touch on problems in Formula One. So I'm talking to an audience here in London. I think everybody here knows Formula One racing. This is what's generally referred to as the pinnacle of motor racing. You've got these very, very fast cars able to go from 0 to 100 miles per hour and back to 0 in less than 5 seconds. And you have teams spending huge sums of money on developing these cars. And come race day, there's actually a fair bit of analysis that goes into solving the problem of winning that race. So as regards what's called race strategy, so pit stop strategy. In fact, let's say, for 3 years, I worked for one of the F1 teams and as their race strategist. And so I've got very good experience as to how these companies are solving these problems. And whereas, let's say, some 15 years ago, you had, let's say, a grizzled race engineer sitting on the pit wall and trying to look at just lap times and infer whether it was the right time or the wrong time to come in for a pit stop. I mean, increasingly, we've got very fine-grained data about, telemetry, GPS data accurate to within 60 centimeters, and this at a rate of, let's say, 40 hertz, coming off all the cars, telling you to a very high level of accuracy where each car is at every point in time, and then being able to normalize for things like to disambiguate between two dominating effects regulating a car's performance. On the one hand, you have tire degradation, and on the other hand, you have the fuel effect. So the effect of carrying on board a certain amount of fuel. And the fact is that teams can use all that data to disambiguate between these two effects, to look at how gaps are changing between, let's say, leaders in the race, and then after that to work out what's an unoptimal stopping problem. And the fact is, in Formula One, your decision on when to stop is very much contingent on everyone else's choices. So you have to solve everyone else's problem, and there's a great deal of recursion involved. But the point is that whereas people used to defer, teams used to defer to someone with a great deal of experience in these domains to solve this problem, that has fundamentally changed. So when I first started getting involved in this problem, it was back at the very end of 2005. And I was approached by, at the time, the Renault team. And on the back of a little bit of analysis that I did, they come in to be their race strategist. And I took leave of absence for my PhD at the time at Harvard. And we had a wonderful season that year. We won the championship. And after that, I've since left F1 in 2008 and everything. We've been doing this. But the fact is that the level of sophistication that has been brought to bear on this problem is rather fantastic. And I should say, speaking to, let's say, the 80-20 rule, the gains that we were able to make in that first year, let's say back in 2006, were huge in the way of our capacity, say, to predict when teams would come in for their pit stop. But the fact is, it's very much an arms race in F1, which means that other teams got savvy to the fact that this kind of data was being deployed and analyzed in a certain way. And increasingly, the advantage, let's say, that one team had over another became commoditized. And let's say, the last 20% of the gains were something that was very, very difficult to extract. And to the extent that it has been difficult to extract, I would say that there are just a few teams in Formula One right now that are doing things that are, let's say, much more sophisticated than everyone else. And I think those advantages constitute actually, let's say, sustained competitive advantages as compared to their peers. So, cognizant of the time, I'll skip some of the nicer visualizations and go straight to this next bit of the talk. So this second case study has to do with a very different part of Formula One, and it's one that many people don't know anything about. And the fact is that teams competing in Formula One spend huge sums of money on developing their cars. And I mean, at the peak of Formula One development budgets, you had Toyota, for example, that in 2004, Forbes reported that they spent almost $500 million in that one season. So, yeah, things have come down a fair bit, but you still have teams spending anywhere between 150 and 250 million US dollars a season. And about 90% of those development budgets are being absorbed by aerodynamic development. So something about aerodynamic development that you should know about in F1 is that it's very, I mean, you might imagine that an F1 car, so this is Toyota's car in its wind tunnel in Cologne. The aero of an F1 car is extremely complex. And so you have these wonderful aerodynamicists who have many, many years of experience in trying to work out, let's say, how to optimize airflow over a front wing, over a rear wing, but you have so many complexities that it's very hard for them to know what will provide a gain. So largely the way that these projects take place is you have between 1 and perhaps as many as 4 to 6 engineers who are working together, designing models in CAD, and these models in CAD are validated, if you will, in computational fluid dynamics simulation, so in CFD, or in the wind tunnel. And all they're looking to do is get downforce at the minimal cost of drag. So they're looking at maximizing the CL points, if you will. It's a nice univariate measure, which is the amount of downforce that you get per unit of drag. And what's rather amazing here is that an F1 team, let's say the aero department of an F1 team, over the course of a year, will develop as many as, let's say, 2,000 components, aerodynamic components. And out of those 2,000 components, which take anywhere between 4 and 16 weeks to develop, you have about 95 to 97% of those components fail. By fail, I mean they don't meet, let's say, a threshold CL value that means that it will yield a performance gain on the track. And so what we were looking to do here is, well, is there anything about how the work is being carried out, about the data that's naturally acquired, about, say, latent data within these F1 teams that could yield an advantage, that could tell us something about ultimately what will succeed and fail in the wind tunnel. And so what F1 teams, even though they're relatively small companies, if you will, I mean, the largest F1 teams have on the order of 500 to 600 people. They're extremely well instrumented. They spend a great deal on IT. And so it was relatively easy for us to get very fine-grained data about who was working with whom, in what measure, on what projects, to get quite a bit of data about, let's say, the pattern of collaboration between these engineers. And what we try to do is understand how do these inputs, in some way, and the history of all the projects that have taken place over, say, a multi-year period, how does all that data, what does that data say, if anything, about the output? And it turns out a great deal. So for a large category of projects, for about 70% of the team's, let's say, product component portfolio, we were able to estimate and everything with about 4 to 6 weeks lead time and with relatively high accuracy, whether something would fail or succeed in the wind tunnel. And the implications then for resource allocation would mean that if you could say with relatively high certainty that something is going to fail when it gets to the wind tunnel, then teams could kill the project now and redeploy those engineers on another project. And so that's a way to effectively increase your yield rate. And for some teams that were able to do this, that we got gains of, well, it was effective gains between 12, 15, and 18%. So the 3 teams at which we did this. There are also implications in this analysis for organizational design. So this is an idea, actually, that we first heard of from a few people that we know at Google HR. And so what they're doing is really trying to understand, well, what is the right promotion strategy at Google? So they're trying to see what departments or what tasks should someone have done for them to be, let's say, to become an effective manager. So you're really trying to understand, let's say, what are the right covariates and everything for estimating what a good manager is, for being able to work out who a good manager is going to be. And we try to apply this to this same data, but in terms of the proxies that we had. And so we looked at this more from the standpoint of cross-collaboration across teams. And this is an absolute mess of a graph, but what you're trying to see here is on the y-axis you have a proxy for communication intensity between teams. So actually what you're seeing here is the actual components, but these are components, these are aerodynamic components on the one hand, but it's a communication intensity across teams. So many of these components actually require the interfacing of multiple teams in order to see out development. So the only communication intensity that we're capturing here is across teams. And on the y-axis, we have the level of, let's say, connectedness across components. So the fact is that we can estimate in a wind tunnel what the contingent performance dependencies are across parts. So we know, for example, that if the airflow over a front wing is going to impact the airflow over the rear wing. So that gives us a way to measure the degree to which the performance of one component is contingent on the performance or related to the performance of another component. And in complex product design, this is a graph that's often looked at to see whether or not, let's say, there's alignment between product dependencies, interrelations on the one hand, and teams. And you roughly want things to be on that y is equal to x line. And so we looked at it just in this sense, but we never looked at this, let's say, as part of the analysis. This was really ex post analysis to see if we could validate it in line with some of the findings in academic literature. And so you might say that, let's say, this is suboptimal. Well, what we did, this was one of the teams, on the back of some analysis related to looking at who was working with whom and collaborating with whom and what measure, we suggested to them some small tweaks in terms of the level of integration across teams and breaking up teams and collapsing teams. And over the course of a 52-week period and everything, this was what we had before, and this is what we had after. And what that translated into, so that dotted line is a counterfactual, but this is on a renormalized scaling, what the performance gains for that team were up to a certain point. So you're seeing weeks here on the x-axis. And then after that, you basically see real data from that red point. There are actually two things at play here in that red point, because on the one hand, there was this organizational design bit, but on the other hand, there was the early warning bit that I talked about before, where they're actually increasing their effective yield rate. So this is in the context of Formula One, but the fact is that this applies to a host of other problems. And one very exciting project that we're working on right now is to do with Crossrail. So if you're a Londoner, I'm sure you've heard about Crossrail. It's one of the largest infrastructure projects ongoing in the world today. These are huge trains that are going to run across central London. They're building under some of the most expensive real estate in the world at the level of anywhere between 25 and 40 meters underground. And these are much bigger than, let's say, much bigger trains than what you're used to, let's say, with the London Underground. These are 200 meter long trains. They're absolutely massive. It's quite something. And what we're working on is trying to, well, as you might imagine, with a project where they're building these vast tunnels under London, where there's one, so much real estate, two, there's already a very crowded, under London, given the tube, given Network Rail, given Thames Water assets, you have a lot of stuff that's already there. And at the same time, London, for better or worse, is built on clay, and a lot of it in relatively soft clay. So when you build something, then things move. And what they've done as part of this project is lay down about 200,000 sensors that are generating a great deal of data about the way in which the ground is moving. And we are taking all of that data, and we are working out, one, we're trying to forecast how the ground is going to move on the back of how the ground is currently moving. But we're also trying to be smart about how they're collecting data. So the fact is that there are these 200,000 sensors that have been laid in the ground. A lot of these sensors, some of them are automated on the one hand, but the vast majority of them amount to manual monitoring. So they require individuals to go out and to point a laser at a prism and to see the degree of change. And for many of these sensors, the current, let's say, monitoring program requires them to measure things once a day or once every 12 hours or at a frequency as high as once every 6 hours or so. And so what we're trying to do is try to make sense on deploying resources just with where they're needed. But the larger point here is that the gains that we're able to do in all these domains, I mean, we're not geotechnical engineers. Nobody on our staff is a geotechnical engineer. And yet, we can solve these problems because, in large measure, because the data is there. And it doesn't require a great deal of domain expertise. So what am I saying? I mean, is this the source? Is data then the source of a sustained competitive advantage? Well, yes and no. I mean, one of the points I'm trying to say, why a lot of individuals, why companies should be very excited about this, is because there are huge opportunities to use data and to find efficiencies. In all likelihood, companies will be able to the extent that they're not right now, will be able to do much more and much more with less with data. At the same time, I mean, I think what we're trying to get at is like the sustained competitive advantage will come in building data assets smartly, in measuring the right things at the right frequencies and for long enough that you can build more sophisticated models. And ultimately, it's going to amount, I mean, I think the Netflix prize is testament to this, that, I mean, for those of you who know about the Netflix prize, I mean, you had, it's a recommendation system problem, and on the back of this relatively large data set, the prize was awarded to the team that would be able to find a 10% improvement in product recommendations. And what you saw was that loads of people applying very simple, generic machine learning approaches, say, were able to find 7, 8% gains. It was that last 2% that required a great deal of domain expertise, required a lot of people to bring together a number of different approaches to the same problem to address their weaknesses. And I think ultimately that's that's what data science will have to do. It will really require people with a great deal of domain expertise to interface with people who have a great deal of expertise in, let's say, non-parametric modeling. But to start with, 80% of the gains are available for very little effort. Thanks very much.